Erasmus exchange program at KU Leuven. So I was in Belgium a few months, something like 12 years ago, even more, 14. Wow, time flies. And then, okay, I enrolled in a PhD program at the Italian Institute of Technology. After that, I went to, for a long visiting period, a couple of years at the Nanyang Technological University in Singapore, like pursuing my research. After that, I graduated, and then I went to Harvard University for my postdoc, for my first postdoc. After some time there, I came back to Italy. Now I was a postdoc there for a few years, and now I'm assistant professor. Especially, I am at the Bio-Robotics Institute of Scuola Superiore Sant'Anna, which is not in Pisa, but is in Pontedera, which is the house of Piaggio. You know, the Vespa scooter is where they are made. And, well, actually, it used to be a 60,000 workers factory, and now it's only 3,000, so a lot of space is available, and this is where we set up some years ago. I specifically work in the artificial hands area, where you can imagine we deal with artificial hands, and where I founded recently my lab, which is the Robotics or textile robotics lab, and I do my research there. Okay, so I told you, I work in the artificial hands area, and I am fascinated by the human hand. The human hand, there are many quotes around, but this is one of my favorites because it's by Maria Montessori, and having a 2-year-old kid, I got very familiar with Maria Montessori, who's an educator, and she knows about kids. But she says that the hand is the instrument of personality, the organ of intelligence, individual will. And this is really fascinating. I mean, this is particularly true for us, for Italians. Now I'm stuck with 2 things on my hands, otherwise I would be gesturing even more. So I think this is on purpose. But through the hand, you don't only interact with the world, because you shape, okay, the world around you with your hands, but not only, because you also sense the words, because you touch things around you. The sense of touch is one of, I mean, our senses, and it's very, very powerful. But not only with your hands, you also communicate with each other. Okay, you tell things, you interact. Okay, also not through direct contact. So the end, I think it's. I mean, I hope I was able to tell you about my passion for the human hand. But there is a but. What if you cannot use your hand anymore for any reason? Okay, maybe you lost your hand. You have a medical condition like a stroke or a spinal cord injury, a brachial plexus injury. There are countless of medical conditions that prevent you from using your hand. And as a result, you are, they say you are disabled because you are not able anymore to do things around you. I particularly love this TED talk by Professor Uher, because he says something really, really great. I advise you to watch it if you didn't. It's from 2015. And he says that a human being can never be broken. Okay, a human being is always a human being, and it's the technology that is broken. So if technology might not be adequate enough to help this person to express at the maximum of his potentiality, okay, of his potential. And I think it's a great concept. So it's the artificial environment, the artificial surrounding of a person that should be healed, that should be fixed to make every person, to give every person the same means to participate to the society, to the activities and so on. So I think this was very inspiring for me. So okay, so moving forward. I recently was working a lot with prosthesis, following this path, following this concept, as I already told you. The first question you might ask you is, well, do we really need hand prosthesis? Okay, there are I mean, a prosthesis is an artificial tool that is attached to the body, and but it's a tool. Okay, you never feel a prosthesis part of your body as when you cut something with a pair of scissors. It's a tool. Okay, you never feel the scissors part of your body. Okay, so it's an imperfect tool. This is what to say. But hand prosthesis, I mean, is a temporary solution, okay? The future will be definitely hand transplantation, okay? In this case, we just substitute a missing body part with a working one. Problem is, we are getting, researchers are getting there, although, okay, they provide better functional outcomes than prosthesis and hand transplant. But the point is that the recipients experience multiple episodes of rejection. It's like from 65, it's about 85% of having one episode of acute rejection. It's like huge, okay? For kidney transplants, we are below 10%. So it's not yet there. So yes, we do need hand prosthesis so far. And it's something that has been pursued since long. And so let's look what a prosthesis does. A prosthesis is designed to substitute missing body parts, okay? But their function, okay, this is very important. There are in the market several dexterous prosthetic hands and advanced controllers to let people interact with these devices. These are just a few of them. The point is that what I noticed in my research is that the wrist function is often overlooked in research. Although the efficient use of hands strongly depends on the wrist, because it's the last element of the kinematic chain that is deemed to orient the hand in space and finally puts the hand in the right place to manipulate objects. People that use prosthesis do not have an active wrist most of the times, and people do tend to compensate this missing degree of freedom by motions of the arm and the body. And this leads to put large forces on the anatomy, okay? You have to really change your posture, your trunk, your upper limb entirely to adapt to this missing degree of freedom. And this might lead in the long term to risks of residual limb pain, musculoskeletal complaints, and overuse syndrome. So this is bad. And we need, so this is to tell you, we need wrist prosthesis. The point is that we have very limited space to place an active wrist prosthesis. Okay? Ideally, the wrist can be considered as a 3 degree of freedom joint, okay, if you consider the arm pronation supination as part of the wrist. So it's very complicated to put something there. So one of my recent work was to design a quasi-passive wrist design that basically allows you to orient the space to the object, exploiting environmental constraints, thanks to a mechanism that locks and unlocks the wrist. And basically, it's very much clock work engineering, so I had to really work with the tiny components, but basically there is a motor that drives a pin and locks and unlocks the wrist. I show you how it works. So basically, does it work, this idea of locking and unlocking the wrist? Well, basically, we see that a person using and not using this wrist drastically changes his body posture while manipulating objects, okay? This is just a passive degree of freedom, which is a spring around which the hand moves, and when you manipulate an heavy object, simply the wrist gets rigid and you can lift objects. And it's a very basic principle, but it's very functional, okay? People with just this passive added degree of freedom of the wrist were able to reduce compensatory movements, which is a very interesting goal. Okay, this was just to tell you a little bit of my research. But the human hand is not only efferent, okay? So it's not only the tool with which to which you send motor commands and you move, but it's also a perceptive organ, okay? There are indeed more than 17,000 receptors on the hand, which are a lot, okay? So there is also all the afferent pathways that sense the environment and give you a lot of information about it. And among them, the mechanoreceptors are those that deliver information about hand environment information interaction. Okay, there are they tell you about object properties, how the contact forces are distributed, what are the shapes of surfaces, what is the friction properties of the object. So it's a very complex organ. And okay, these are basically the receptors that are in the hand, the mechanoreceptors in the hand. There are several. Some are responsive to long and prolonged stimuli. Some are responsive to short, to the transient events. So basically they fire only when there is a change in the contact pressures. So there are several. So it's a very engineered system. But how does our brain use this information? Well, basically, when your brain, you think to move your hand, or any limb in general, you send a motor command, okay? And normally, because of the sensory information is processed, it's rich, the brain cannot process it in real time. So most of the times, the movement starts in open loop. Okay, but how the brain deals with this open loop? Well, basically, the brain has an internal model of what is the limb and what is the environment, and it makes a prediction of what the brain expects to be the sensory input. Okay, and then our brain collects the sensory feedback and compares the actual sensory feedback with the predicted one to implement corrective actions. Okay, this is exactly what it happens when you lift a bottle that you don't know its content. Okay, maybe you think it's heavy. Okay, and you grab it and you overshoot with that, meaning that you made a prediction on the physical properties of the object, and it's wrong. So you do an overshoot, but then you learn. The next time you lift it, you know. And you already modeled, okay, its properties, and you do that for the next grasp. Okay, you cannot process all that information. Although there is one single information that is processed in real time by the brain, and this is called the discrete event-driven sensory motor control. So basically, the discrete information are used by the brain to divide the manipulation task. Okay, so basically the brain divides the manipulation in sub-goals, in sub-tasks, and these sub-tasks are signaled by transient mechanical events, because it's very quick and it's little information but essential. Okay, and what are these events? Are basically when you touch an object, when you lift it from the table, when you replace it, and when you release. Okay, and this is very quick information that is processed by the brain in real time. Okay, but what happens? Okay, I told you, this is when there is a mismatch between them. You implement motor correction. But this is a nice working principle. But what if this mechanism is somehow compromised? And this may be due to several conditions. Okay, you might have this rupture in this communication system in the brain due to a stroke, or in the peripheral nervous system, and so you cannot implement these corrective actions anymore. So basically, your hand is still capable of moving, but since you cannot control it properly, you cannot move it. Basically, that's why we developed together with Leonardo, a PhD student in my lab, a simple, very simple device, which is this one. Okay, basically it's a glove with ultra-thin piezoelectric sensors, so they are sensitive to the transient events, transient pressure events. So basically they fire only when you touch, and then they go basically to zero, and when you release, and then they basically go to zero. And we deliver vibrations corresponding to these haptic events. Okay. Okay, there is basically the same as you do when you type in your cell phone. Okay, you press it and you have a vibration with a vibrational motor, and that's it. So, like, technologically, it's simple. It's not easy, but it's simple. But okay, is it working? We did a couple of preliminary tests, and I hope this video works. And this is a person with a brachial plexus injury. That cannot feel anything on his hands, okay, and he's doing some tests. Okay, he was asked to transfer an object, which is a fragile cube. Okay, if you press it too much, it breaks virtually. Okay, it makes a clack mechanism, and then it's counted as broken. And with minimal training, so he came, he tried it for 5 minutes, and he was able to transfer more objects without breaking them, and basically the completion time remained more or less the same. Okay, this is wearing the glove with the stimuli on, wearing the glove with stimuli off, and with the bare end. Okay, so and this is, I think, super interesting. But let's see at the next one. So we also measured accurately the contact forces between the hand and the object, and how he was able to lift the object. So basically here we were measuring grip force versus load force. What does it mean? It's a measure of coordination, okay? When you are coordinated, you start lifting an object while you are still grasping, okay? Because you are able to modulate the contact force with the object while you grasp it. While instead, if you don't trust your hand, first you squeeze it, and this happens with people with prosthesis or with people with sensory impairments. They first grasp to a very high safety margin, and then they lift, okay? And as a result, you have a very non-linear, okay, shape of this grip force versus load force. So basically, first it means that here they start pushing, and then they start lifting. While, on the other hand, wearing the device, which, again, doesn't provide you continuous contact, continuous feedback, but just a very short vibration at the beginning when you touch the object, the coordination is much better, okay? So this is basically, this makes people lifting while they are still grasping the object. And I think this is an incredible result, because it's a very simple piece of technology and provides you a very simple information, but it's relevant, it's highly relevant, and the brain is able to integrate this into the motor control. And more interestingly, we are affecting the motor side only by applying a sensor, so a sensory stimuli. And this is interesting, okay? Because a lot of devices are out there that give you motor aid, motor stimuli, and they impact, of course, much more than this one on the motor side. But this is really interesting, I think. It's an interesting result. Okay, but let's switch to big things. This was a project that is still going on there, and I want to talk to you about this big European project that they had. I was lucky enough to participate. So I was part of the consortium. This was an Horizon 2020 project with, I think, 10 partners in Europe, and we were the coordinator. Professor Christian Cipriani was the coordinator of this project. I work as a postdoc here. What did we do? Well, the project was about prosthesis, but they were in the direction of having osseo-integrated prosthesis, okay? So we want to put technology closer and closer to the human body. And this is what we did. So basically, this was a very recent work. So we implanted a screw in the residual part of the bone of ulnar radio of a person, of a participant, but not only. Since we had this connection between the inner part and the outer part of the body, we took advantage of it, and we also used them as a gateway to connect both to the nerves, to collect neural control signals, okay? And so what are the efferent control signals that went to innervate the residual muscles? And also, we connected through calf electrodes to the nerves, to the afferent nerves, okay, to be able to send back sensory information to this person, okay? So we took advantage of an extraordinary mechanical stability of an osseointegrated interface, and we also used it to connect to the control system of the person. So first, the person could use, immediately after the surgery, to train to generate the signals through a virtual interface. And this was really a few weeks after the surgery. And then, after some time, this is what she was able to do, okay? What is she doing? Well, basically, she's probing an object with a spring inside, and we are in the hand, there are force sensors that transduce the force signal into nerve impulses, and she was able, just by probing with her prosthesis, to correctly put these objects in along increasing stiffness. So she was able to perceive the stiffness of the object, which is impossible to do with a normal prosthesis. So she made use of this technology. And most interestingly, she was able to don and off the prosthesis by herself in a very quick way, in a very reliable way. Okay, this is often a problem because the osseointegrated interface avoids the need of a socket, which damages in the long run the soft tissues and might get several problems. So this is how the prosthesis looks like. And these are other tests that we perform with the same fragile objects, which are pretty nice. Yeah, I just wait to go to the end of this video. Yeah, and this was the first implant. We performed the second last summer. So we were able to perform 2 implants with this one. And we got a very great acknowledgement by the scientific community. We got the cover by Science Robotics, so I wanted to show off a little bit. Sorry about that. But I mean, I really enjoyed working in this project. And this is a piece of information that I put in my background. But, okay, am I a prosthesis guy? Not, I am not. I don't feel like I am into prosthesis. Why? Because I like very much working with exoskeletons. And this is where actually my scientific path started. So I want to go in this direction. Is it an original passion? Well, it is not. And this was the very first attempt of making an exoskeleton in the world in 1967. And the idea was to make the great dream was to make a symbiotic unit with the alacrity of man's information and control system coupled with the machine's power and ruggedness. Okay, it's great, and I mean science fiction. It's rich with exoskeletons and so on. But actually, this didn't work at the time. This is a nice animation, but this was a nice piece of steel. Although it was a great starting point for research, and from here, like the science and engineering of exoskeletons started becoming more and more pursued. Okay, but I have a personal preference that is that when robots interact with people, having a soft interaction is preferable. Okay, of course, when this is particularly true when when the softness is coupled with robustness and reliability. Okay, so you have to. I mean, you can do that to a soft robot, or you cannot do that to a rigid robot unless you want to pay too much money. Of course, there are pros and cons of this approach. Okay, a rigid robotic arm cannot reach much better performances than this one. There are pros and cons of this approach. Okay, how I started to tackle with this principle? Well, during my PhD here in Italy and in Singapore, I started encoding softness in a rigid system through control. Okay, so you can program a robot to be soft, okay, to behave like a virtual spring, and I designed a wrist robot this is an exoskeleton, a grounded exoskeleton for wrist rehabilitation. Okay, this is a very much younger version of me I think it was 2013, and where we deployed this wrist exoskeleton to a pediatric hospital in Genoa. And basically, you can encode softness by telling the motors how to behave. But okay, I thought, okay, this is really interesting, but I want to go a bit more like on the field. And I started working on exosuits. Okay, exosuits is a concept of exoskeletons where the rigid frames are completely removed, and in their place you put textile frames. Okay, and in this case we started working on a hand and an upper limb, so an elbow exosuit, where basically it's a piece of fabric, it's a glove, where there are cables routed along the glove itself, and they are able to pull and so extend or flex the fingers of the hand. Okay, and as you can see, this is a path towards getting softer and softer in the interaction with a human person. And this was particularly my contribution. I designed the very first version of this elbow exosuit, which is a cable pulling and pushing the elbow. Okay, but after that I developed some skills, but I said, okay, I want to investigate this even more, and this is where I joined the VC Institute at Harvard. So during my postdoc, basically I went to Cambridge and I joined the Harvard Biodesign Lab. They are those who basically made the very first exosuit, which is the group of Professor Conor Walsh. In that group, I joined a research team that had the goal of designing a pneumatic exosuit. Okay, what is it? Basically, it's a device that is powered by air. Okay, so also the cables are removed from close to the human body, and only a pneumatic actuation is provided. And this is where, when I joined the lab, we were here. So basically, there were these nice gloves made of silicon, okay? And with me, we started using textiles as the material to which provide actuation. Okay, so the textiles, I told you before, they were the frame on top of which to build the actuation. But during my research, I also discovered that textiles can become the actuators themselves. How comes? Well, I tell you. I had to discover that textile is not just one thing, but there are several types of textiles out there and several ways of making them. And by leveraging this knowledge, and the textile industry is super developed, okay? So there are several, like the technology there is very, very developed. Okay, so we can take these final products and build actuators for human augmentation. How to do so? Well, basically, we started studying the mechanical properties of textiles. And for example, if you take a piece of woven fabric, which is the one you have on your trousers, okay, this is a woven textile. Basically, it's made of yarns crisscrossed in this way, so along weft and warp direction. They are basically overlapping one to each other's. And as a result, if you take a piece of this fabric and you stick it into a universal testing machine, you basically get a kind of linear behavior, or, well, anyways, it's a isotropic behavior. Okay, so if you pull along warp and along weft, you get a quite rigid behavior. And they're used for these properties in a lot of fields. Okay, they are used in construction fields as support structures. Okay, you inflate a big structure and they can keep building on. So textiles can be very powerful. But if you take a piece of knit fabric, which is the one of your pullover, but also of your technical sport apparel, they are made of technical knits. Well, they are very elastic, and interestingly enough, they are not isotropic, okay? They display a very large anisotropy depending on what is the side you pull. And of course, it depends on the material it's used and so on. Is it possible to exploit these properties? And this, very interestingly, is a property that comes in a piece of hardware that is basically two-dimensional, okay? Because the thickness of the textile is really neglectable with respect to the other two directions. So it's something that it's really interesting by the engineering point of view. So how to make an actuator out of them? Well, very simply, you take two layers, okay? You stack a knit fabric on top of a woven fabric. You take your sewing machine, or you tell your PhD students to start to learn how to sew by hand and to make them. You stick a balloon, okay, a bladder inside this, and as a result, you have your actuator, because you exploit the anisotropy, so the material contrast, the contrast of mechanical properties to make this actuator. Well, and then I show you how they work, okay, don't worry, don't be scared. But you can do even more, because it's a 2-degree, it's an almost two-dimensional structure, so you can pile them, you can make a lot of them. So you can stack a stretchable textile on top of a non-stretchable textile, on top of another non-stretchable textile, and put balloons inside. And the result you can get several degrees of freedom, several degrees of actuation within the same, basically, bulk, okay? And so we made these devices as fingers of a robotic glove, and by inflating these chambers, okay, we could get different degrees of actuation. So basically, you remember we had two pieces of one layer of inextensible textile, another layer of inextensible textile. Okay, if you put a balloon inside of that and you inflate it, the balloon has to be oversized. Okay, so all the pressure has to be distributed to the textile and not by the balloon surface. In that case, it becomes a rigid beam, a straight rigid beam, okay, if you pressurize it. And this was the case to get hand opening motion. While if you inflate the balloon that is between the high stretchable textile and the low stretchable textile, well, basically, the stretchable textile will try to expand more than the bottom layer, and as a result, you have a top layer that expands more and a bottom layer that doesn't, and you have a curling motion, a bending motion, okay? And you can actuate hand closing with this device. Okay, so we also characterized them, and we were able to generate forces enough to manipulate daily living objects. But I want to show you how it worked. Okay, so this was a video that we made characterizing a knit fabric, you can see, and these were our machine shop, okay? For me as an engineer, I was shocked at the beginning to have to learn how to use them, but this is how they look like, okay? They are super soft, super tiny, although they are really powerful, okay? So here we are inflating the strengthening, so okay, the rigid beam, and here we inflate the other chamber, the one that generates motion. Okay, this is another younger version of me, less young version of me than the one you saw before. And this is how it works. Okay, so basically it bends and it curls the finger. So, well, in this case, we are exploiting the underlying biomechanics of the hand. And by applying, if we have a curling actuator, I mean, the fingers will not curl as an octopus tentacle, but will bend along the human anatomy. Okay, so we exploit, this is interesting, okay, because we exploit the frame, the natural frame of the body. So we don't add mass to the system. So the robot doesn't have to move itself before moving the body, because its weight is really limited. So, so this is, I think, really interesting. We did a clinical study with spinal cord participants, and these are the plots showing that the participants got better at manipulating objects, at generating forces with their hand, but it's very nice to see a person using it, because it's really nice. Okay, this is a person with a spinal cord injury, incomplete spinal cord injury, C6 spinal cord injury. He has some residual motion, but he could not lift heavy objects. And this is how the device worked. So basically, there was a PhD student there pressing a button when he said close, and they closed the hand and open again. Okay, we were still working on the human-machine interface, but I mean, we had the PhD students again. And he was able to lift quite heavy objects. Okay, this is a can full of root beer, I think. And yeah, it could actually lift and use objects, okay? And he was very happy doing so. You could not only lift like heavy objects, but you could also use the same device also to manipulate tiny objects, because of course there are two different problems, okay? Because maybe you can be able to grasp a large object, but maybe not a tiny one. This didn't help him to get luckier with the dice, but still he was very happy to take part in this. And this is also something I would like to talk about, because I mean there is dealing with real people and trying to help them is part of the non-monetary compensation you have working in this field. So I really enjoyed being close to our study participants, who gave us a lot of suggestions and so on. So I mean this is I think to be remarked. Of course, during my stay there were also some, I started some evolution of the device. Basically, we could get rid of the Carlin octopus-like device and implement something more anthropomorphic. Okay, we could get bendable areas and stiff and basically non-bending areas, so to better mimic and better transfer forces to the human hand, and also integrate sensors there. This is a very basic application where there was a touch sensor on top of the finger, and it was a very tiny textile-based sensor that triggered closing and opening when there was contact. So basically, for the person in this case, was enough to touch an object, and the hand started grasping it. So it was an evolution towards better human-machine interface. And this is how it works. Basically, you touch, and the device started curling. Okay. We also had a guy who came to our lab. This is Bill Gates, who gave us some advices, and so it was particularly nice and scary to give him a device that he had to wear on his hand. And his lawyer was taking the picture, so I was like. Joking, of course, but it was really fun. We also had Jeff Bezos trying the device, but he didn't want us to take any picture. So he took pictures of us. So I guess I am by his bed in this picture, but he didn't share them with us. Okay, but you all know that what you put in papers is never. It's always the nice side of it. Okay, but dealing with textiles, you deal with a lot of frustration and a lot of failures, and this is because textiles are not easy to manufacture. Okay, ask your grandma. When you put a balloon inside a piece of textile that you sew together, the seams might break, the textile itself might break, and we had a lot of popping, and people like last week I had all the lab mates that got scared because I had an actuator that exploded, and it's of course this is a source of problems, because if you give this system to a person at home and it breaks, it suddenly breaks, you have to replace it, go there. So stacking textiles together is problematic because of the connection. Okay, so basically all the problems come from the connection. Is there a way to get rid of it? Well, I mean, if you want to couple textiles with different material properties, you cannot fuse them together. You cannot put rigid components because you don't want to. Is there a way to get rid of that? There is, and we were the first in the world in 2021 to use 3D knitting to make actuators. What is 3D knitting? 3D knitting basically it's getting a thing in apparel industry, because you actually program a machine, and after a couple of hours you have a full piece of garment with all the material properties you want, because it can vary the stitches. So basically it's a knitting, so you cannot get woven textiles out of it, but you can use unextensible yarns to make some sides, you can use elastic yarns to make others, you can have a more dense stitch on some sides, you can have a looser material on the other. So basically you can mechanically program the behavior of the textile locally in a structure that doesn't require you sewing with a sewing machine. And my PhD students are very happy about this. And this is in collaboration with a colleague of mine in Turkey. So they have this machine and in the process of acquiring a new one. Are we on time? I mean, okay. So basically, you can get a similar structure. You can get several layers of structures with something more extensible and something less. And you can get properties that are similar to ones that I've shown you with an integrated production method. So basically, you go there, you program the machine, you say print, and in 20 minutes, you have this actuator that you stick a balloon inside, and you have a pneumatic actuator out of a machine, which is very nice. And we proved that, okay, it was pretty bulky, but we proved that we could achieve similar performances to the ones previously shown, which is, I think, very interesting. Okay, let's wrap up. I spoke about my background in prosthesis, and I spoke about my background in soft textile-based exoskeletons, but how comes I'm here speaking for long? So why did I tell you so? Well, basically, these were all the ingredients that I used to bake my ERC proposal, okay? And it will start next month, basically in March, so I didn't start yet. So I don't have too much to tell you about it. So invite me in a couple of years again, and I will extend this part and get rid of the introduction. But okay, this is what I will do. So the concept that I wanted to capture was this one. Okay, so you got this message. Disorders of the nervous system, either central or peripheral, are primary causes of disability. Okay, there are so many people in need of assistive devices. When you have such a problem, you can do sensory motor rehabilitation, and most of the people go through it and get much better. Okay, but it's not always fully effective. Okay, as a result, people need to wear or to bring with them assistive devices for the rest of their life. Okay, we give devices to a person. As a researcher, we give a device to a person, and they improve, like we did with that clinical study with a glove. But then you take them away from people because it's a research device. But again, even if it was a device on the market, this person has to deal with this device for the entire life. Okay, so and wearing that kind of device was very complex. So human-machine interface is not always that great. But I will tell you something more. To deal with that, the wearable robots stand at the forefront, okay, of scientific research to help people with neuromotor impairments. And there are still open challenges in the field, okay? For example, we have rigid exoskeletons that are incredibly great for helping people moving, okay, to provide a lot of forces, and they are the only ones that can help people walking again after being paralyzed, okay? But on the other hand, they are quite heavy and quite bulky. As a solution to this problem, exosuits started being a research field, and they are lighter and less bulk, but still they have problems of speed and complexity. You've seen the pneumatic actuator, so the pressure with which I inflated the fingers was the maximum I could achieve, so I just opened a pressure can, basically, and that's the speed, and they are rather complex, okay, because they require routing the forces along the human body. On top of that, all these devices are connected to the human body through straps, through elastic bands, and so on. And although they allow people to use them, they are not ideal because you want to ensure rigid connection, so you want to tighten them as much as possible, but on the other hand, you don't want to tighten them as much as possible because you stop the blood flow, you can cause damages to the soft tissues, and so on. So you will agree with me saying that they are not ideal. And most of these, although most of these devices have sensors to close the control loop, because you need to close the control loop to control a robotic device, not so many of them convey this sensor information to the user, okay? And the user needs sensor information to interact with the environment. This is what I told you at the beginning of this presentation. Also for a lower limb, okay, because you need to know if the terrain is structured or non-structured and so on. It's great that the exoskeleton knows, and a lot of technology is there to let the device know, but how to convey this information to the person is still an open issue. What I want to do with my project is to solve these issues in a way by making a soft and streamlined system that is able to provide fast and efficient assistance connected to the user through a very stable human-machine interface and providing rich sensory feedback. The key to do that is through osseointegration, okay? I've told you what it is. Basically, it was born for dental implants and recently is being used for prosthetic applications, okay? So it's safe and stable. We can connect these implants to the bone without having major medical issues. On top of that, and smartly enough, we can, this technique opens to a way of providing sensory feedback through the mechanism of osseoperception, okay? This is particularly interesting. Why? The bones themselves, in the periosteum, there are several vibrational sensors, okay, mechanoreceptors, and it's through them that you sense low-pitch noises, okay? When you are at a concert, you feel the bass with your body, with your full body. This is because of these properties of the mechanoreceptors. Plus, the bone is a rigid mean, and sounds travel fast through, with minimal dissipation through rigid means. So if you apply vibration to a local point on your skeleton, it travels through your bones to your skull and to your inner ear, and you can hear sounds. Okay, this is. There are commercial devices that let your skull vibrate to hear music. They are very getting more and more diffused, and they are the basics of osseointegrated hearing aids. Okay, you can see people with deaf people who can hear again. It's not a recently discovered mechanism. Okay, Mozart in the late age of his life was deaf, and he connected a piece of a metal rod to the piano, and he used to bite it to hear the sounds. Okay, thanks to this mechanism. Okay, the sound traveled through the metal rod to his teeth. Again, rigid mean, and then they went to the skull. So it's possible to do that. Okay, so what I want to do is transcending the paradigm of wearing robots by developing these three basic technologies, okay? So I want to increase my knowledge in pneumatic actuators, coupling them with some elastic, non-linear elastic structures to provide powerful yet fast actuation. Of course, I have to develop the osseointegrated human interface to connect the exoskeleton to the human body, to the human skeletal system. And finally, I want to exploit this connection with a skeleton to provide enriched sensory feedback through this mechanism of osseoperception, either by stimulating local sensation, eliciting local sensation through the vibration to the sensors in the periosteum, or by delivering them to the inner ear. The path is long, so basically along my ERC grant, I will have to to achieve all of these before to make the first implant, but at the 5th year, it's planned to make the first implant on a human being. So I have to push because the path is long. I'm planning to build a team working on this, and I want to exploit my collaborations. Okay, I have people I work with. Recently, I'm starting talking also with Bernardo Innocenti here at ULB because he's an expert in human implants. I want to tell you that I'm hiring. So if you guys are looking for a position in this field, please let me know if you know someone that might be interested. And just to finish, I like to tell that some of the European Sustainable Development Goals can be tackled with this project, because I want to improve the quality of life, so this goes towards good health and well-being, advancing assistive technology, so this will strengthen the European technological assets, so I'm very happy of doing that. This goes towards the industry innovation and infrastructure, and of course, restoring independence of people who lost it due to a medical condition goes towards reducing the inequality, and so again, going back, fixing the artificial environment that surrounds a person, helping them not to be broken, okay? And yeah, that's it. Thank you for your attention, and yeah, drop me an email if you want.
So I have an official communication from BrIAS that is, I want to mention that no PhD has been harmed while doing the research that has been presented.
Yeah.
Nor Bill Gates.
No, nor Bill Gates, especially.
Jokes aside, I imagine that there are questions, so we are here to torture you, so please go on.
I did connect my dancers to quite a lot of objects. And then in this learning curve, I guess, something we saw always is that the more they, even when practicing, sometimes they become spontaneous and they can do everything with that stupid object, whatever they like. And the next day, they think too much and suddenly they can't anymore. As if you can compare it with ice skating. You think too much about ice skating and suddenly you fall because suddenly the body doesn't has this connection anymore. Maybe a strange question, but can you see this kind of connection, spontaneous or subconscious, that suddenly allows things? And if the patient thinks too much, or do you see that same thing happening?
I guess we could discuss about this for an entire day, but I try to be brief. Because, yeah, I totally see the point, and this happens with every technology that I told you, and prosthesis, those that feedback glove, and also this extension. I think that I kind of replied already with my slides, because I think that your brain has to model the technology itself. And so the more you train, the more you get better at it. And as soon as you stop thinking to it, so as soon as you master, so as soon as you made an internal model of the technology, then you will be good at using it. So I think, and it's an open discussion topic with people using prosthesis, because we always try devices with 10 minutes of familiarization, and this doesn't tell you anything, I think, because people have to master the device, so you should let them use it for long before. This is a problem, because you don't have 10,000 hours. This is the rule, no? The 10,000 hours rule. you can be called a master in something if you trained for 10,000 hours. I guess your performance cannot train 10,000 hours for every technology. But I think it is what it is. So the brain has to adapt. So if you leave enough time to people to train, to get familiar, you can get better and better results. Better than those you see also in, I think, in research papers. So yes.
But what I also see is sometimes when the machine becomes too complex or very complex, then it's less subtle than a stupid thing. A friend of mine was born without an arm, and he had it since childhood. Always this, he's very cute, very small, and then he has this little arm, and now, but he's so used to saying when he caught a fish, he would say it was this big. So it was completely integrated, completely. He speaks like this with one, and you don't even see that there's a fake arm. Sorry. Is there so also again there in the connection between something complex and something between, yeah, there's somewhere. I don't know.
Yeah, but I agree with you. Again, it's a big topic, no? Because the more something is complex, the more you need to train, and that's why we went also in the direction of giving you like short-lasting vibrotactile feedback, because that one can be easily used by the brain to integrate it into the control scheme. And embodiment is another thing. I mean, there are also things that come that are pre-programmed in our cortex. Okay. Also, people who were born blind. There were experiments to say that people who were born blind participated in an experiment with other blind researchers, and when they talk about, for example, steering a cup, they talk while gesturing the steering motion. Okay. So, like, the more, I guess, I think that the more something is anthropomorphic, so the closer you are to the natural shape of the body, the easier it is for your brain to integrate, to embody that technology. I think it's going to be very complex to control supernumerary arms, for example. Although people are going in that direction, I think it represents a cognitive burden, so you really have to study to do that. While the closer you are to the human body, the easier it's going to be. My 2 cents, but we can discuss a full day about that.
Anya, is the microphone working again? Test. Huh? Okay.
So
Shall we switch or shall I?
I will just stand there and then read the question for you, and then you can put the mic. So you had, first of all, you had some compliments from Carl that he said he said bravo, and then Bettina Wallington said great project. So I just wanted to share that. And also for myself, it was very impressive. You have one question from Alex Partridge. With current osseointegration, the areas that are connected to are fairly static, such as dental implants and leg prosthetics. It seems to me that you will be attaching to more dynamic parts of the body. How do you plan to accommodate for the increased movement of skin and muscle around the connection? Okay,
yeah, this is a great question. Again, we can yes, I move. Again, we can spend a lot of time talking about that. But basically, I came to know that when you do this type of connection, like for lower limb prosthesis or upper limb prosthesis, basically you fuse. You pierce the skin, okay? So you make a hole in the skin and then you make a hole in the bone, but then you like make the skin layer thinner in a way that the skin fuses with the borders of the bone, so that there is no basically contact between the skin, or very minimal contact between the skin and the implant. In this way, there is no more the motion of the skin around that area, and this is how it's possible to stabilize the implants. So basically, we will try to do that. meaning that we will make some models, and then we will see if this translates. But this will be the way to do that. So basically, prepare the skin in a way that it fuses to the bone in that particular point. Yeah.
Okay, thanks for the very nice talk. I hope the mic is working. I had a question. When I was looking at your soft finger exoskeleton that you were showing, I had the impression that the pneumatic part was actually detached from the finger most of the time, and it was mostly pulling on the most distal phalanx of the finger. Is that correct?
It is correct,
Okay,
yes.
yeah. So I'm wondering if it's not more comfortable to have an exoskeleton which basically attaches to all of the phalanges of the finger. And then related to that, is it also possible to make it with the current design such that you now have a relatively constant radius of curvature, so that the radius of curvature changes over the length of the finger?
You can, yeah. To answer to your first comment, yes, you can decide basically, because if you have a bending structure, I mean, since that you can program the behavior, the local textile properties, you can do whatever you want. Okay, with of course, with some variability that is intrinsic in scientific research. But yes, you can do that. So basically, it depends on what you want. Here, in this particular case, it's in the case of my intended device, it is actually what I want to do. I want to contact only where the implants are, so that the skin is left as free as possible from any interaction. Plus, with that kind of behavior, you have only pushing and pulling forces on the implants, which is, I guess, even better, because if you have shear stresses on them, it might compromise the implant. So this is an extra pro that I can get. Okay, I hope I replied.
Yeah, cool.
Thanks.
Thank you.
I will first read from the chat. So Fabrizio Da Bene says extremely interesting, and Alex says fantastic, thank you. I will also be attending in March and would love to have further conversations about this. So you'll meet each other then, I guess. As far as my own question, so my background is in human technology interaction. So I work with robots, with exoskeletons, and these are all devices that are like not inside you. So I was just wondering, if you do a pilot study like what you showed on your slides, but also what you're planning to do, what are the implications for your participants? Like, how long do they keep that? And because I assume it's just, you know, for like a pilot study, and then you take it out again, or how does that work? I'm not familiar with like doing implants in a scientific study.
So well. Great question, and the European Commission gave me 21 ethical deliverables for this, so I have to be really committed. The point is that yes, the implants will stay there, so they are meant to be permanent implants. Of course, if anything goes wrong, I budgeted also for removal, but ideally the implants will be as stable as possible, and they will be at around the 4th year of the project, and then I will integrate all the technology developed up to that point and give it to the user, and have the last year to re-engineer everything to make it working for the participant. Ideally, we keep with this participant an open channel, because we want to give him or her a working technology for the rest of his life. So we will offer continuous support even after the project is finished. The other project that you've seen about the osseointegrated prosthesis, this person is still using the prosthesis, so we are still in touch with them after the project finished. So that's the idea, to keep working with these people. And of course, if anything goes wrong, we have insurance and we have everything to have them covered. It's not, I mean, it's not only a technical issue, but it's also a psychological thing to make sure and to clear, because people, how does the image of themselves change? It's something that we don't know, okay? And it's something that we need to explore. I think it's also an interesting part, because you kind of like connect something in a permanent way to a person. And in science, scientific research, you always have the right of going back, okay, of quitting whatever you're doing. But in this case, in case of a permanent implant, is something you cannot do at will. Okay, one day you wake up and say, I don't want it anymore. But I guess this is, I mean, the risk this project may cause are much like balanced by the benefits that these persons can get. I was talking to a hand surgeon that told me that people who cannot move their hand anymore go to him asking to have their hands removed. And if you think about, I mean, yeah, you say, yeah, you then have it removed and then you have a prosthesis that works well. But we were talking about taking away a piece of the human body, and I think that it's huge, and it's psychologically it has a huge impact. And on the other hand, an implant like this one could be much less impactful psychologically on people. So I think it's also could be a solution to this problem.
Thank you.
Thank you.
Okay, very short technical question. When I saw your the actuators made out of wool, and you said you have problems with the seams sometimes going off or going on. Have you looked into the kite surfing kites? They reminded me of it because they have usually there's like a bladder, it's called, in it, which you pump, and then it has a really high pressure. And they have different shapes of wings, they called the wings, and they have like C shapes or D shapes. And there you have a bladder and you pump it up all the time, and then you deflate it already also. And they usually never really break. Like the problem is, or when there is a problem, it's because you dump the kite into, I don't know, a rock or something. But usually they don't have the problems, I think, with the seams there, and I was wondering if you had looked into that, or if that would maybe be some sort of ideation help support.
Yeah, well, like in this field there are several approaches to this, to the pneumatic actuators in general. If you want, so the one that you mentioned exploit heat sealable textiles, because in general they are piece of fabrics with an internal substrate of its sealable material, plastic material. It's a polymer that fuses when you apply heat, and you can, on top of that, you can also apply even a thicker seam, which is actually another piece of its sealable textile to actually seal it. The point is that this material layer prevents you from having large deformations of the textile, so basically you cannot exploit anymore the material properties. You can exploit the shape, so you can pre-program the shape of the textile to be, for example, an arc or a finger, and then deflate it. And when it's deflated, it's flat, and when you inflate it, it will bend and will go back to the original shape you pre-programmed. They are a bit thicker, though, so I think it's not going to be the right direction for me for my application, because I want something that is as streamlined, because there are examples of similar concepts for shoulder exoskeletons, and there you need larger forces and you don't really need a sleek device that is below your armpit to lift your shoulder. But on top of my hand, this is a design choice I made at the beginning. So on top of my hand, I want something that is very thin, and the bladder you can put inside the textile layers is really, really thin compared to the sealable textile, so it will be thicker. So it's a choice of, to me, it was an optimal choice for the end. But other people might have different opinions about that.
I would have another question. We saw all the pneumatic fingers, but what is the pumps and all the things that are behind it? How much of how much weight, how much will that add to a person that will have to wear it on their bodies as well? Or what's like the background system, I would say.
Yeah, again, that's another big issue we need to face, and in general, all the actuation stages will have to be somewhere. I envision making something like a backpack or a belt mounted system. So I want, for example, the air source to be a can rather than having a pump there, so that you can switch it like a battery and you can go ahead for longer without having the sound of a compressor. But again, it will depend a lot on the participant, because if the participant will be on a wheelchair, for example, then I have much less size and weight constraints, because I can hang the actuation system to the wheelchair, and since this person will be using it for most of the time during the day, this won't be an issue. On the other hand, if the person has brachial plexus injury, meaning that she will have lost only the use of the upper limb, in that case I will need to optimize in that direction. But this project will be very much, since it's going to be a demonstrator on one participant, it will be very much oriented towards the participant. And I already started looking for the participant, which will be the patient in 4 years. So it's like that. Thank you.
Just a question that arises due to what you just said. How will you choose the participant, and where is there some criterion and some ethical issues in the choice of the participant?
Okay, this is a big point, because it's the most important element of this project. Most of the people with upper limb disability that could be candidates will be, I mean, there is a huge pool of potential participants among people with stroke, but on the other hand, there might be a lot of side effects. So ideally, I'm looking for a participant with a very long life expectancy, so ideally young people, and there are a lot of young people who had motorbike accidents, for example, so people with brachial plexus injury or spinal cord injury, and most of them are male for some reason. I'm looking for someone that is potentially very active and want to compromise with a permanent implant in their life. So I think I'm moving towards this direction. Ethical implications, sure, there are several. Since it is a single participant study, so ethical issues will be dealt depending on the participant, him or herself. So I cannot make any guess now. I hope I answered to the question. Not so much.
Yeah, with regard to ethical issue, I was more thinking of regarding the choice. I choose this person instead of this person. I will. This might be a dilemma and might cause issues with regard to those two people.
This is right. I guess as in medical research, like for the for the amputee in the other project, I will make inclusion criteria. And basically, this will give me a scoring system with which to be as objective as possible, so that I cannot cherry pick the participant based on my personal preferences. Of course, we have to meet criteria that will be defined together with a clinical partner, which will play a huge role in this project. So I will draft the inclusion criteria in a way that I'm not biased towards this or that participant. Yeah, the ethical issue is twofold. Because somehow you can advantage someone by giving them an implant, but on the other hand, you might cause them a lot of problems. So it's, yeah, if you cherry pick, you don't know if you are doing good or bad. I mean, I hope I'm gonna do much good to this person. But being a clinical trial, you never know. So yes, I will make sure to have an objective system to choose the right person. Thanks.
I have a quick question. I've had clinical experience of young patients losing their limbs and having to take care of the aftermath of that in intensive care units. And my question is, are minors excluded from your...
I think so, yeah, because the bones are still changing. So I'm not convinced that an implant would be accepted. And I mean, I don't even know if minors can have a dental implant or a bone implant. So in general, I think that I need the skeletal system to be fully developed before to make any implant.
Yeah. It's interesting, but one would think that they would have more flexibility to adapt to it, or the ability to accept it more because of the specific physiology, I think.
A very young person might develop the best skills, again, to go back to the other question, to master the technology, because their brain is much more plastic than ours. And so I think that they would be perfect users for these technologies. On the other hand, the constraints are very, very rigid, but it's something it's worth investigating. I will check with Bernardo, who is an expert in this. So I'm in the right place.
I'm pretty sure that we will continue making you questions today and for the rest of your stay. So for your information, you will leave us for 1 week and then you will be back. So you are leaving on Friday, yes. Being away for a week, and then you will be back for other 2 weeks. So as I already said other times, the Brussels Institute of Advanced Studies, it's a place where, first of all, we meet and we speak. So if you want to spend more time with Leonardo, you have just to contact him. He has also put his email there. So he will be most of the time here at SAAS or at BEAMS at Bernardo Innocenti's research group. And with this, I would say that for the moment we close here this first talk. We go for a well-deserved coffee, and then we come back for our second talk. Oh, shall we do in 10 minutes at 3:30, 3:35? Okay. Okay. So, can everybody hear me? Let's see our technical. Okay, perfect. So we can start with the second talk of today. That it will be Zemer Artasani. So, or how we call everybody Art. So Art, I had to read because I never remember. I always call you Art. Sorry. So Art is one of the PhD students of our research lab here at ULB and of the research lab at VUB directed by Professor van der Boer. Actually, is in co-tutorship between myself and Bram, and is working on a subject on which we have worked for the last few years, that is robotics for construction. So I leave him the stage.
Thank you very much for your introduction. Well, I would like to thank everyone being here to... Okay, let's adjust a bit. Fine? Yep. So I would like to thank everybody for being here today to listen to my presentation. Yes, so I'd like to repeat again my name. I am Zemer Artasani. And today I will be speaking about how we can use multi-robot systems for heavy load manipulation. Well, before I even start my presentation, even though Professor Garone already mentioned our team, I still want to show a bit our faces. So basically, what I want to mention is that there are three groups working together for the BrIAS project. And the BrIAS project has two versions, 1.0 and 2.0. In the 1.0 is this PhD who worked on it, and now it's me who is working on the version 2.0. Well, now let's start to my real presentation. Well, the motivation behind this work is construction, and the reason is because construction as an industry is lagging behind other industries in terms of productivity. And in particular, if we compare it to industries such as, for instance, manufacturing, well, we can clearly see also in this graph, there is almost 2 times higher production, higher productivity in manufacture than in construction. And of course, the question that follows is, why is this so? Well, to answer to this, we'll go to each industry separately. And we begin by manufacturing industry. In the past, everything was done by manual labor. Today is done with robot arms. While if we go to the construction, in the past everything was done by human laborers with aid of cranes, and here in black and white, while nowadays it is done still in the same way with human labor, with aid of cranes, but now the picture is just in colors. So what this tells us is basically that we have to do something in terms of robotization. However, there have been quite a lot of attempts in the past to have or to robotize certain processes in construction. Mainly, the robots developed come from industria, but as well also from research. Well, mainly they follow rigid assumption, meaning that they need a rigid robot because they need precision. So the robot should be very, very big, like this one here, for instance. The other assumption is that they say, okay, construction is well-structured environment. Well, that's certainly not the case. For instance, this type of robot here and this one here, they have rails and they have to install them all the time, and so that takes time and is not efficient. Other solutions basically use either small blocks or custom-made blocks. So basically to fix all these issues that are present, we have some designing guidelines. And the first is that we need first to overcome the assumption of rigidity. So we don't need to really focus too much on having just one robot that is very big to give us precision. While on the other hand, what we want is basically to have a lightweight robot that is able to handle heavy loads. And of course, it could be good also if we could explore using devices that are already in the market. This is cost efficient. And we would like a flexible solution, meaning that we can use that robotic system in different scenarios and different tasks. So what we propose is a robot system. Actually, it's not this one here, because this one failed to go to the market because it was super big and it took too much to be installed so that it was not feasible to be used in construction. So that's why we propose a solution that is a multi-agent system with complementary capability. And by complementary, I mean that we have two different robots. We have a crane here that's there to take care of the heavy load, and we have a robot arm or a precision unit that is there for precise manipulation of the object. Of course, during this PhD, what we are doing is that we are trying to use this robotic system in a specific use case in construction, that is building walls with heavy blocks. And of course, this system, to be going to the market, has a lot of steps, but what we are focusing now is in these two steps: modeling and control design and experimental validation. And I will be speaking mainly about these two parts during my presentation today. It is important to distinguish also when humans are doing this process in construction. Well, you have an operator and you have another mason. This operator is operating the crane, so pick up the block and then moves toward the other mason. And then the other mason basically grabs the block and places it on the wall precisely. So we can distinguish three phases. The first phase is that they work independently, and then they have the phase in which the human grabs the block, and then they work all together. So we also have the same thing with the robots, and we want to reach the same thing with the robot. So what does this mean? It means that we have first to start with independent control, so controlling these systems individually. We begin that with the control of cranes. Well, the type of cranes that we have investigated are overhead cranes, knuckle cranes, and boom cranes. And we have noticed in the literature that there is quite a lot of gap in terms of modeling completely these type of systems, but also in development of control strategies. So our purpose is here to develop a general methodology, how to model, but also how to control such systems. And during my talk, I will mainly focus on this type of robots, or this type of crane that is called boom crane. And of course, the methodology shown here will be then easily applied to other types of crane as well. And it's nice that for any mechanical system, one as such here, we can represent the dynamics in this nice form consisting of the joint inertia matrix, Coriolis matrix, friction vector here, gravitational vector, and of course the control inputs. But this matrix here in front tells us that this system is actually a special type that is called under-actuated system, because it has less actuated joints than what it has degrees of freedom. And so the first step was to develop a nonlinear controller for this type of system. And then, of course, we proved the stability of this system and stability analysis. And more details can be found in the papers. Here is a numerical simulation that we show for our crane. And basically, we compare it to another type of controller that is linear quadratic regulator. And as you can see here from the video, but also here on the graph, we can see in red there are quite a lot of oscillations of the block, while our control scheme is able to dampen those oscillations in the blue. Of course, so we said next, okay, can we do a bit better than this? And then we explored doing feedback linearization. Feedback linearization is a technique that is quite famous for rigid manipulators, but actually we would like to do it also for under-actuated systems. But of course, this is not fully possible to do because, as I told, it's an under-actuated system. And then we developed such a controller. I'm hiding all the math behind. Well, and then through this part here on the controller, where we're able to somehow affect the unactuated joints, and like this to have basically less oscillations. But before I even show you simulations of this part, I would like to introduce you to model predictive control scheme. That is a scheme basically that takes into account the constraints, and as the name suggests, basically, it uses model for prediction and then solves an optimization problem to compute the sequences of input, which then we apply at each step. Of course, then we do a numerical comparison between these two schemes, partial feedback linearization and model predictive control. Well, from this graph, we can see here that both these two control schemes actually are quite good. Well, but to understand why we prefer to use model predictive control instead of partial feedback linearization is actually here. Because if we look here, we see that we are way over the constraints or the limit of saturation of the actuators. And that is very important for practical implementations. Well, there are some drawbacks with MPC. One of them is computational time. It takes quite a lot of time. So that's why then we move toward the explicit reference governor. There is a constraint control scheme, but now this does not require any online optimization. And it's an add-on unit that is put basically on top of a system that is already pre-stabilized, for instance, with the controller that we saw before. And it is composed of two components, dynamic safety margin and navigation field. Well, navigation field just tells you in which direction you have to move. Dynamic safety margin tells you how fast you can change the reference without passing those constraints. Well, one good thing is that we can put constraints, and that can be constraint on the joint limits, can be constraint for safety, such as reducing the oscillations, but also obstacles. And in this simulation here, we show our ERG. Basically, we ask our crane to go to 2 points in the space, and so here on black is represented the obstacle, and the controller basically is capable of avoiding hitting that obstacle while making sure that the constraints are satisfied all the time and that we have very few or very dampened oscillation, which is our goal. Of course, behind these all theoretical aspects, we also developed prototypes. In particular, we have this boom crane here that is a small scale prototype, and we have this overhead crane that we have just here on the lab. Well, as I was speaking about control of robots, we also did control of the cranes, also did control of the robot arms. Here, in particular, we have developed a new type of trajectory-based ERG that is called saturation-aware trajectory-based ERG. What it does is basically, or what is important to know is that it gives you a faster response, but also it gives you, let's say, it's less computationally, less computation effort it requires. And what it does is basically just that it represents the constraints as intrinsic components of the non-linearities of the system dynamics. Well, then comes the intermediate phase. That is basically the phase when we have to grab the block. And the reason why a human is able to grab a block is because he can see where the block is. And to give this same feeling to the robot, what we do is we use a camera system. And of course, also camera systems can have their own problems. That is, they can have packet losses, they can have noisy measurements. And so this can lead to unpredicted trajectory tracking, but also impacts. And this is what we want to avoid because the blocks that we are planning to use are very heavy, around 120 kilograms, and they can damage your robotic system. So what we use is an extended Kalman filter with intermittent observations. And what it does is basically it filters the measurements and takes into account the fact that when you have packet losses, you do not give measurements that do not make sense. So then we implemented this into our real setup, and these are the results. And we can see here that the robot arm is basically able to track such an object, such a block moving. Well, this is a nice step, and then the next step was to basically grab a static object. Well, in this case, it is oscillating, but we have an algorithm behind that tells us when the oscillations are reduced, when then we can go and grab the block. And basically, now comes the time where the robot basically goes and grab it. Well, I cannot show it now, but okay. Then, Yeah, believe me, just believe me, yeah. Then the next important thing is that, okay, you are in a construction environment, but you want to know where the target wall is, because there is where you want to place your block. And so also here with cameras you can have problems, because in long distances they can give you errors in measurements, etc., and you can have dust and rain. So how to overcome this problem? Well, to overcome this, one solution is to make use of the robotic arm, because it has inside some sensors which are quite precise on the joints, and so like that we can basically reconstruct we can reconstruct the position of the target wall with respect to the robot. And this is how we do it. And of course there is a detection algorithm behind this, so that we save the robot from being damaged. Now, having all of this, we can go to the next step, that is using these two robots in cooperation. But of course I spoke to you about modeling the cranes, modeling the robots, but then we have to join them together, and that we do through constraints, in particular holonomic constraints. Then we can rewrite the dynamics of the system in this form, and this form is very interesting because we can use it to develop the control laws. Here we have proposed this nonlinear control law, and we can prove global asymptotic stability with this Lyapunov function candidate, but also we have developed a method how we can basically do the differential kinematics of such a closed chain system, and then of course use it to calculate the inverse kinematics to pre-plan trajectories for the robotic system. And here I'm showing an experiment of our small-scale robotic system, where basically we are having a block here that is 2 times heavier than what these small robots can handle alone. So this is a way we could prove the feasibility of such a concept. But then of course we want to do better. What we do is we go toward constraint control schemes, in particular explicit reference governor. And now what I will show is basically for the IVAR robot, that is a bigger robot than what we saw before. Well, now we'll go a bit more into details about the ERG. It is composed of navigation field and dynamic safety margin, and this navigation field has 2 main components: attraction term that attracts the robot toward the goal, and the repulsion term that basically pushes away the robot from passing the constraints. Then we have the dynamic safety margin. The dynamic safety margin tells you how fast you can change the reference to still be within those constraints. Well, for that you need a pre-stabilized system, so for that we need the controller. We need the dynamics because we need to simulate, and then we simulate over the time t, and then we check the distance between constraint violations, and then we use that as a dynamic safety margin. And this here basically tells us how fast we can change the reference, but also it tells us that in case in the next step we will have constraint violation, we don't change the reference at all. And here is the experimental results. Here we have this block that is 70 kilograms, and this robotic arm can only handle 14 kilograms. This is a crane that we have here on the lab in my left. And basically here we were able to prove that with explicit reference governor we are able to place a block on a wall that is heavier than what the robot can handle precisely but also safely. And of course with this experiment our job doesn't end here, because there is still some research to be done, in particular about when we have contact, because when we place the block on a wall we will have contact, and how to manage contacts to not destroy the wall, etc. But another important step that I skipped during my presentation is how we can grab a block. So how we can grab a swinging block that is super heavy with a small robot without breaking it. Then we also want to introduce constraints, more complicated ones, obstacles like this, but also to put humans in a loop so that we avoid, for instance, harming a human that is operating nearby where the robot is. Then we're also doing a bit of SLAM, 3D SLAM, and for this part mainly will be responsible the vision ETRO group. Here we just recently started working on on a path planning algorithm, because we can use it for the navigation of the base, which we plan to add to this system, in particular this Husky base. And yes, with this I conclude my presentation, and I would like to thank you for your attention.
So thank you, Art. Just to add a few things. So this research project is financed by Innoviris, FWO, and by a series of other minor source of fundings that we obtained over the years. And it's, as Art clearly said, it's in collaboration with the group of Professor van der Boer, but also with the ETRO, the group of computer vision at VUB2. And since the beginning, it's a project that has been carried out in collaboration with the industry, and in particular with the company Basics, that is the largest construction company here in Belgium. So I imagine that there are questions for the speakers, so please go for your questions.
Thank you for your presentation. It was very interesting to see how you showed at the beginning. You have this person doing well, applying the glue. I forgot the name. The mix, and then the other one operating the crane. And I was just wondering, because well, in my background is human robot interaction, and now we're looking at, in your scenario, you're actually replacing this task. I can imagine why, because probably we will not have enough workers, etc. But I was just wondering if the things that you are making now, could they be repurposed if you would only want to change one of the others? Because I can imagine if there are construction workers that want to get back to work, but they have like an injury or something, but maybe they could still operate the brick movement, let's say, and maybe then they could collaborate with your robot that is putting down the bricks or doing the last step. I was just wondering what your thoughts are about that.
Yeah. Our intentions are to not really replace the human completely or put it out of the loop, but the idea is mainly to replace the human work, which means all the, let's say, tough tasks will be done by the robot, while humans are there to supervise the work mainly, because construction is one of the industries with the most fatal accidents. So that's the purpose in this sense. Yeah, that's what I would like to say.
Thank you. Thank you. It's very interesting.
Thank you, Art, for this nice presentation. I want just to jump back in on this question, how the supervision will be done then? How the human will supervise two robots on these construction sites?
Okay, so how a human can...
Yeah, how, like, maybe you don't have the question right now, but how the supervision of the human will be?
Well, basically in the sense that it will check the quality, maybe, if there is, because you need also, let's say, calibration of your robotic system, etc. All these steps that human on a loop to really verify, give a green light that you can start or you can stop.
On this, like, what is the stuff that you would like the robotic system to be able to perceive in the environments, like humans, obviously, but I don't know, maybe there is something else that I might have missed.
Yes, it is important, because why we want to do SLAM, because it is an environment that is unstructured, meaning that it will change, but if it is today like this, tomorrow it will change, because you're building walls, you're building things, and there are people around. So it is important for us to be able to have, or to be able to, let's say, localize our robot. So that's why we need SLAM. Also, 3D slam
solution for simple blocks, so for blocks that are standard without interlocking capabilities or self-aligning capabilities. All these things were completely shut down by both producers of the block and architects. And then after that, we arrived to the design that you have seen. So Art has not spoken about the design, but the design of arriving to this idea of the two robots took a certain number of iterations. We also did a preliminary economical analysis because we wanted to do something that, assuming that the research is over from the economical viewpoint, must be much more convenient than hiring just 2 people and using a crane. And after that, we finalized this first design and we start with the control. Now I would say we are in a phase in which there is still feedback with the company, but we are in that phase of developing the technology itself. I expect, we had some feedback anyway, we are in constant contact. We had a series of feedback. I expect in 1 or 2 years when we will have something that is actually able to build a wall that we will restart an almost day by day interaction because, okay, the wall looks well, looks badly, our workers are scared or not of having a machine like that around and so on. So we are in that sweet spot where it's mostly academic research, but everything started with the companies and everything will end with the company. So it's really something like that.
Thank you. Thank you for the clarification. Sorry, I did not know there was a whole trajectory before that, but it's very interesting. Thank you.
Any more questions?
I think this is going to be, I mean, this is an open question for the future, but would it be interesting to, I mean, have human and robots cooperate? I mean, I envision having a robot for lifting the high load while the human operator could do the fine placement. So is this a direction that, I mean, could be interesting or something that you might want to tackle in the future?
What we will be doing is basically to have the robot and the crane cooperating together while avoiding any human working together with this system. But of course, the system, we will give to the system, let's say, enough safety to operate around humans, but not with humans. Because, working with a human, well, humans are not as robots, they cannot be programmed, so problems can happen and injuries can happen. And then that could be, I think, a bit of adding more complexity in terms of, having safety on terms. But that's why I think also in future we will just be working mainly while avoiding cooperation with human and a robot. Yeah.
Any other questions?
If there are no other questions, I would close here for today. I would thank again the speaker. And also because even today we went a little bit overboard with the time, which is a good sign because it means that there is interest. And thank you again to everybody for being here. And for the seminars, see you next week. But I will not stop repeating that the BrIAS season is not something that it's a series of seminars on Thursday afternoon, but it's actually an ongoing activity where we meet, we speak, we have curiosity, and we spend around the coffee some hours with the fellows, the other researchers of the local groups, and whoever else wants to participate. So thanks to everybody again. Good afternoon, and see you on Thursday with our direct at the VUB. As you know, we do one week in one side and 1 week on the other, also to mix even more the groups and the various competences. So thanks again to everybody, and see you on Thursday.